Imagine holding a grain of sand in your hand and realizing it is older than the Earth itself, older than the sun, older than the very disk of gas and dust that gave birth to everything we see in our sky. Now imagine that this ancient relic is not resting quietly in a museum or buried deep within a planet, but is instead racing through our solar system right now, a cosmic messenger from a time before our world even existed. What if an object passing silently above our heads was forged before the sun ever ignited? What if it carries a story from another star, another era, or even another corner of the galaxy? For most of human history, the solar system was imagined as a closed, almost sacred arrangement. The sun at the center, planets moving in orderly paths, comets as occasional intruders from the outskirts, but everything ultimately belonging to the same family. We grew up with the comforting idea that our cosmic neighborhood was self-contained, formed from a single cloud of gas and dust 4.6 billion years ago, evolving in relative isolation ever since. That picture, elegant and simple, is now quietly collapsing. Modern astronomy is revealing something far more dynamic and unsettling. Our solar system is not an island, it is a crossroads. The moment scientists confirmed the existence of the first interstellar object passing through our solar system, the rules changed. That discovery was not just about a strange rock with an unusual orbit, it was a philosophical turning point. It told us that material from other star systems can and does wander into our own. The boundary we once imagined around the sun has turned out to be porous. Space is not empty and orderly, it is busy, chaotic, and filled with debris from countless stellar births and deaths. Objects like 3I, Atlas force us to confront this new reality. They do not move like ordinary asteroids or comets born in our system. Their paths are hyperbolic, meaning they are not gravitationally bound to the sun. They arrive from interstellar space, pass through briefly, and then disappear back into the galaxy, never to return. This behavior tells a dramatic story. Somewhere, long ago, around another star, a violent event occurred, perhaps a close encounter between forming planets, perhaps a gravitational slingshot from a giant world that ejected this object into the cold darkness between the stars. Once expelled, it began a lonely journey that could last millions or even billions of years. Drifting through interstellar space, it would experience temperatures close to absolute, bathed in faint starlight, slowly accumulating cosmic radiation damage. In that deep freeze, time almost stands still. Chemical reactions slow to a crawl. Surfaces remain largely unchanged. In many ways, interstellar space is the universe's ultimate preservation chamber. This is why the idea that 3I, Atlas, could be older than our solar system is so electrifying. If it was formed around a star that existed before the sun ignited, then this object is not merely foreign, it is ancient. It would be a survivor from an earlier chapter of the Milky Way, predating the Earth, predating the planets, possibly predating the sun itself. We are not just seeing a visitor from another place, but potentially from another time. Age, in this context, is not measured by appearance alone. It is inferred through motion, composition, and context. The velocity of an interstellar object matters. Objects born in our solar system inherit the sun's motion around the galaxy, but an object formed elsewhere carries the signature of its parent star's movement. When astronomers measure an unusually high relative speed, it suggests the object is not just passing through it, has been wandering the galaxy independently for an extraordinarily long time. If 3I, Atlas, has been traveling for billions of years, then it has witnessed eras of galactic evolution we can only model on computers. It may have existed when the Milky Way was younger, when heavy elements were less abundant, when star formation followed different patterns. In that sense, it becomes a physical record of cosmic history, written not in light but in matter. This realization transforms interstellar objects from curiosities into priceless scientific assets. Telescopes are not just observing rocks, they are intercepting messages. Each trajectory, each spectral signature, each subtle chemical clue is a sentence in a story that began long before Earth formed its oceans. We are used to studying the past through photons light that has traveled for eons to reach us. But here, for the first time, we may be studying the past through touchable matter, matter that has physically survived the journey. That changes how we think about exploration. Traditionally, to learn about other star systems, we imagine sending probes across vast distances, journeys lasting tens of thousands of years. Interstellar objects flip that script. The galaxy itself is delivering samples to our doorstep. They are uninvited, unpredictable, and fleeting, but they are real. They are here. This leads naturally to a deeper and more unsettling idea. If objects like 3I Atlas exist, then they are not rare accidents. They are the natural byproduct of planet formation itself. When planetary systems are born, they are messy places. Young stars are surrounded by swirling disks of gas, dust, rocks, and ice. Planets grow by collision and accumulation, but not everything settles down. Many objects are flung outward, ejected forever by gravitational encounters with massive planets. Over billions of years, this process must populate the galaxy with trillions upon trillions of wandering fragments. Rogue planets, icy bodies, rocky debris, all drifting between the stars. Interstellar space, once imagined as a near-perfect vacuum, may instead be a graveyard and a museum combined, filled with relics of countless failed worlds and abandoned beginnings. In that context, our solar system is not exceptional for being visited. It would be exceptional if it were not. Every star system plows through this sea of debris as it orbits the galactic center. Occasionally, by chance, one of these ancient wanderers passes close, enough to be captured briefly by our attention, if not by gravity. The second great implication follows directly from this realization. If interstellar objects are common, and if some of them are older than our solar system, then the timeline of cosmic history becomes tangible in a new way. We are no longer confined to studying our own past. We can sample the past of the galaxy itself. Imagine what that means. Our solar system formed from material enriched by generations of earlier stars. Supernovae seeded the cloud that became the sun with heavy elements carbon, oxygen, iron necessary for planets and life. But an object formed earlier might reflect a different chemical recipe. By studying it, we could directly test models of galactic chemical evolution. We could see how the ingredients of planets have changed over time. This is not just abstract science. It connects directly to one of the biggest questions humanity has ever asked. How common is life in the universe? Life, as we understand it, depends on certain chemical elements and stable environments. If ancient interstellar objects show that complex organic molecules formed early in the galaxy's history, then the potential for life may be far older and more widespread than we once imagined. Some of these objects may have passed through countless star systems exposed to radiation, shock waves, and stellar winds, yet still retained complex chemistry. That resilience would suggest that the building blocks of life are not fragile accidents, but robust features of the cosmos. At the same time, there is something profoundly humbling about this picture. We like to think of Earth as ancient, of human history as deep. But an object older than the sun makes even geological time seem brief. It reminds that our existence occupies a thin slice of a much longer story. Civilizations rise and fall. Planets form and erode. Stars ignite and die. And through it all, small fragments of matter drift silently onward, indifferent to everything except gravity and time. The discovery of interstellar visitors forces a shift in perspective. We are not just inhabitants of a solar system. We are participants in a galactic ecosystem, constantly exchanging materia with the wider Milky Way. The atoms in your body may have passed through multiple star systems before becoming part of you. The same processes that ejected 3I Atlas may one day eject fragments of our own solar system into interstellar space, carrying traces of our existence far into the future. In that sense, 3I Atlas is not just a visitor, it is a reminder. A reminder that the universe is older, larger, and more interconnected than our everyday intuition allows. A reminder that the story of our origins does not begin with the sun and does not end with us. Once astronomers realized that objects like 3I Atlas were not gravitationally bound to the sun, the next question became unavoidable. Where did it come from? And how long has it been traveling? The answer lies written in its motion. Every object in the universe carries a kind of fingerprint in its trajectory. Planets trace graceful ellipses because they were born from the same rotating disk as the sun. Asteroids wobble and cluster because they share a common origin. But an interstellar object tells a different story. Its path slices through the solar system at an angle that ignores the planetary plane, its speed too great to be captured, its direction unaligned with the sun's long-established family of worlds. This is not a minor detail. It is a declaration of foreign birth. To achieve such a trajectory, 3I Atlas must have been accelerated by forces beyond our solar system, most likely by a massive planet or stellar interaction in another star system. In the chaotic early stages of planetary formation, giant worlds migrate, stars pass close to one another, and gravitational encounters become violent. In these cosmic pinball machines, countless smaller bodies are flung outward at tremendous speeds, escaping their parent stars forever. Once freed, they become galactic nomads. What makes this especially compelling is the scale of time involved. Interstellar space is vast beyond ordinary comprehension. Traveling from one star to another at typical stellar velocities can take hundreds of thousands, even millions of years. If 3I Atlas originated around a star that formed before the Sun, then its journey may span billions of years. That means it has crossed spiral arms, passed near supernova remnants, drifted through molecular clouds, and survived environments that would destroy most delicate structures. Its very existence is a testament to endurance on a cosmic scale. The velocity of such an object can hint at its age. Older stars tend to have higher random velocities relative to the Sun, having been gravitationally stirred by countless interactions over time. If 3I Atlas shares that high-speed signature, it suggests an origin in an older stellar population. In other words, it may have been born in a time when the galaxy itself looked very different, when star formation was more intense and planetary systems were still experimental, chaotic constructions of nature. This possibility elevates 3I Atlas from an astronomical curiosity to a scientific treasure. It may be carrying information not just about another star system, but about an earlier epoch of the Milky Way. Unlike light, which tells us what something looked like at a distance, matter tells us what something is made of. Its composition, structure, and surface chemistry can reveal conditions that existed long before our solar system took shape. If this object formed before the Sun, then it predates the carefully ordered architecture we see today. It comes from a time when planetary systems were raw, unstable, and violent. Studying it allows us to test our theories of planet formation under conditions we cannot recreate and cannot observe directly anywhere else. This is where the idea of a natural time capsule becomes unavoidable. On Earth, time capsules are deliberate. We bury objects hoping they will survive centuries. In space, preservation happens unintentionally, but on a far grander scale. Interstellar space is cold, dark, and sparse. Without atmosphere, weather, or biological activity, change happens slowly. An object drifting between stars can remain largely unaltered for billions of years. Especially if it is composed of rock or ice shielded beneath a hardened surface, such an object is frozen history. Its minerals may record the temperature and pressure of its birthplace. Its isotopes may reflect the abundance of elements available at the time of its formation. Its surface chemistry may show how cosmic radiation modifies matter over immense timescales. In effect, it is a geological record of another world, another star, and another time. We have meteorites on Earth that are older than the planet itself, remnants of the early solar system. But 3I Atlas potentially goes far beyond that. It may be older than the Sun. That places it outside our entire narrative of planetary history. It becomes a witness to an era we can only infer indirectly through models and simulations. This raises a profound scientific opportunity. If we can analyze the light reflected from such an object in sufficient detail, we can identify its composition. Does it contain water ice, complex carbon-based molecules, unusual ratios of elements? Each answer constrains theories about how planets form across the galaxy. If ancient interstellar objects resemble our own building blocks, it suggests that planet formation follows universal patterns. If they differ significantly, it tells us that our solar system may be just one variation among many. There is also a deeper implication hiding beneath the science. Time capsules usually preserve moments we fear losing. Here, the universe has preserved something far older than memory itself. An object like 3I Atlas reminds us that the galaxy has a memory written not in words, but in matter. Every star system contributes fragments to this archive, scattering pieces of its history into the void. And every so often, by sheer chance, one of those fragments crosses our path. This is a rare moment in human history. For the first time, we have the technology to detect these visitors, track them, and begin to analyze them. We are standing at the threshold of interstellar archaeology. Future generations may look back on this era as the moment humanity realized that the solar system is not sealed, that ancient relics from other stars pass by us regularly, carrying secrets from deep time. In that sense, 3i Atlas is more than an object. It is an invitation to expand our timeline beyond the sun, to see our place not just in planetary history, but in galactic history. It suggests that the story of our origins is part of a much longer narrative, one that began long before our star ever shone and continues to unfold as ancient messengers quietly drift through the darkness. When scientists contemplate objects like 3i Atlas, the discussion inevitably expands beyond origin and age to something even more profound. What these ancient wanderers can teach us about the birth of planetary systems and the potential for life throughout the galaxy. If this object truly formed around another star long before our solar system existed, then it is a fragment from a time when planets were assembling under different cosmic conditions. It becomes a probe, not sent by intelligence, but by gravity and time itself, carrying information across billions of years. Planetary formation is not a gentle process. Young stars are surrounded by turbulent disks of gas and dust, where collisions are frequent and violent. Planetesimals smash together, sometimes growing into planets, sometimes shattering into debris. Giant planets migrate inward and outward, destabilizing everything in their path. In this chaos, countless objects are either destroyed or ejected. The ones that survive intact long enough to escape their star's gravitational grip are the lucky remnants of a cosmic demolition site. If 3i Atlas is one such remnant, then its composition offers a rare snapshot of how planets formed in environments unlike our own. The early galaxy contained fewer heavy elements than it does today. Each generation of stars enriched the interstellar medium with heavier atoms forged in stellar cores and supernovae. A very old object may therefore show a simpler chemical makeup, reflecting a time when the universe was still learning how to build complexity. By analyzing the light reflected from its surface, astronomers can infer what minerals and compounds it contains. If it shows evidence of water ice, carbon compounds, or complex organic molecules, it would suggest that the ingredients for life appeared very early in the galaxy's history. That would be a startling conclusion. It would mean that the raw materials needed for biology were present long before Earth formed, possibly long before our sun ignited. This idea radically expands our sense of possibility. Life would no longer be a late, fragile afterthought in cosmic history. It could be a natural and early outcome of planetary chemistry. In such a universe, the question is no longer whether life exists elsewhere, but how often it arises and how long it can persist. Interstellar objects may even act as couriers of chemistry. As they pass through different star systems, they may deposit material, collide with planets, or break apart, seeding worlds with complex molecules. This process, sometimes called cosmic exchange, suggests that the galaxy is not just a collection of isolated laboratories, but a connected system where matter and chemistry circulate over immense timescales. While this does not mean life itself travels easily between stars, it does mean that the chemical groundwork for life may be widely distributed. The same molecules that once drifted through interstellar space may later become part of oceans, atmospheres, and living organisms. In that sense, studying 3i Atlas is not just about distant stars. It is about tracing the ancestry of the molecules that make up life itself. At the same time, these objects force us to confront the sheer violence of planetary birth. We often imagine planets forming quietly from dust, settling into neat orbits. The reality is far harsher. Planetary systems are forged through collisions, disruptions, and ejections. Every stable system we see today is the survivor of an ancient catastrophe. Interstellar objects are the debris fields left behind. Understanding this chaos helps explain why planets like Earth are both rare and resilient. To survive long enough for life to emerge, a planet must occupy a narrow window of stability. Too many impacts and life is reset repeatedly. Too little material exchange and the necessary chemistry may never develop. Objects like 3i atlas help us understand how finely balanced this process is. There is also a technological implication that cannot be ignored. For the first time in history, humanity has the tools to detect these ancient wanderers. Wide-field sky surveys scan the heavens nightly, tracking faint points of light that move against the background stars. Powerful computers calculate their trajectories, distinguishing bound objects from interstellar visitors. Spectroscopic instruments analyze their composition from millions of kilometers away out. This capability marks a turning point. For most of our existence, interstellar space was a theoretical concept, a vast nothingness separating stars. Now it is becoming a field of study in its own right. We are beginning to map the traffic of the galaxy, to understand how often these objects pass by, where they come from, and what they carry with them. In the future, this may go even further. Concepts are already being discussed for rapid response missions, small spacecraft capable of intercepting interstellar objects as they pass through our solar system. Such missions would allow direct sampling, turning fleeting encounters into deep scientific investigation. The idea that humanity could physically study material older than the sun is no longer science fiction. It is an engineering challenge. These developments also reshape our sense of scale. We tend to think of exploration as outward, as journeys to distant worlds. But interstellar objects bring exploration inward. They come to us. They cross our orbit. They invite us to study the galaxy without leaving home. Each detection is a reminder that we are immersed in a much larger system, constantly interacting with it whether we notice or not. Perhaps the most humbling aspect of all this is the realization that these ancient objects have passed by countless star systems without anyone noticing. For billions of years, the galaxy has been exchanging material in silence. Only now, in a brief window of technological capability, are we beginning to see it. That suggests that our moment in cosmic history is special not because we are central, but because we are finally aware. Objects like 3I Atlas do not shout their importance. They drift quietly, indifferent to our curiosity. Yet in their silence, they carry answers to questions humanity has asked for centuries. Where did we come from? How common is life? How old is the story that led to us? By studying these ancient travelers, we are not just learning about other star systems. We are uncovering the deeper processes that shaped our own existence, written in matter that has been wandering the galaxy since before our sun was born. Only recently has humanity reached the point where encounters with ancient interstellar visitors are no longer matters of chance or hindsight. For most of astronomical history, objects like 3I Atlas would have passed unnoticed, slipping through the solar system silently, leaving no trace of their visit. Today, that is changing. The sky is now under constant surveillance by automated telescopes that scan vast regions night after night, comparing images, tracking motion, and flagging anything that behaves out of place. This technological awakening has transformed the universe from a static backdrop into a dynamic environment filled with motion and surprise. When an object like 3I Atlas is detected, the clock immediately starts ticking. These visitors move fast. They do not linger. Their hyperbolic paths give us only a narrow window, weeks or months at best, to study them before they vanish forever into interstellar space. This urgency has forced a new way of thinking in astronomy. Observation must be rapid, coordinated, and global. Telescopes across the world turn in unison, capturing every photon they can, extracting as much information as possible before the opportunity is lost. Advanced tracking systems allow astronomers to reconstruct where these objects came from and where they are going. By tracing their trajectories backward through the gravitational field of the galaxy, scientists can estimate the regions of space they may have originated from. This is not exact, but it narrows the possibilities. Each interstellar object becomes a data point in a growing map of galactic motion, helping us understand how material circulates through the Milky Way over immense timescales. At the same time, improvements in spectroscopy allow scientists to analyze these objects without touching them. By splitting their light into its component colors, astronomers can identify chemical signatures, water ice, silicates, carbon compounds encoded in faint absorption lines. This technique turns light into a translator, converting distant matter into readable information. In effect, we are learning to read the chemical language of ancient worlds as they pass us by. This capability represents a profound shift in our relationship with the cosmos. For the first time, humanity is not limited to studying distant stars and planets frozen in time. by the speed of light. We are studying objects that have physically traveled through space and time to reach us. They are not images of the past, they are the past itself, arriving in the present, looking ahead. The implications become even more extraordinary. Concepts are already being explored for missions that could intercept interstellar objects at high speed. These would not be massive spacecraft, but agile, lightweight probes designed to launch quickly and match trajectories. Even a brief flyby could yield invaluable data, sampling dust, measuring magnetic fields, or analyzing surface composition up close. Such missions would mark humanity's first direct interaction with material from another star system. This is not just a technological challenge, it is a philosophical one. By intercepting an interstellar object, we would be crossing a boundary that has existed since the dawn of civilization. For the first time, we would be directly studying matter that did not originate around our sun. It would be a quiet but profound milestone in human history. As these capabilities grow, they force us to reconsider our place in the universe. We often imagine ourselves as observers standing outside the cosmic story, looking in. In reality, we are embedded within it. Our solar system is not isolated. It is continuously interacting with the galaxy, exchanging material, energy, and history. Interstellar objects are the visible evidence of this exchange. This realization reshapes how we think about origins. The Earth did not form in isolation from the rest of the galaxy. The atoms that make up our planet, our oceans, and even our bodies were forged in early stars, scattered by supernovae, and mixed into the cloud that became the sun. Objects like 3I, Atlas, are part of that same cycle. They're reminders that creation is not a one-time event, but an ongoing process. There's also a deeper message embedded in all this. The universe is not static, it is not finished. It is still experimenting, still reshuffling matter, still producing new combinations of worlds and possibilities. The fact that ancient objects can wander for billions of years and then briefly intersect with a young technological civilization is not just a coincidence. It is a reflection of the universe's vast interconnectedness. In studying these ancient travelers, we are not merely satisfying curiosity. We are learning how the cosmos builds complexity over time. We are learning how chaos gives rise to structure, how destruction leads to creation, and how the past continually shapes the present. Each interstellar object is a chapter torn from a much larger book, one written across the entire galaxy. And perhaps most importantly, this knowledge changes how we see ourselves. We are not the center of the universe, but neither are we insignificant. We are a species that has learned to look up, to detect subtle motions in the sky, to decode the chemistry of distant matter, and to ask questions that span billions of years. In a universe filled with ancient wonders, that ability to understand, to connect, to wonder may be one of the rarest and most remarkable phenomena of all. When we step back and look at the full picture, objects like 3I, Atlas change the way we understand our cosmic story. They remind us that the solar system is not an isolated beginning, but part of a much older and larger galactic process. These ancient wonders carry with them the history of stars that lived and died before our sun was born, preserving clues about how worlds form, how matter travels, and how complexity emerges over time. In studying them, we are not just observing something unusual in the sky, we are reaching back into deep time and touching the earliest chapters of our origins. What makes this moment extraordinary is that humanity is finally capable of recognizing these visitors for what they are. For billions of years, interstellar objects have crossed star systems unnoticed. Now, in a brief window of technological awareness, we can detect them, analyze them, and learn from them. That ability reflects how far human curiosity and science have carried us. We are no longer limited to wondering about the universe. We are actively listening as it reveals its history. Thank you for taking the time to explore these ideas and for sharing in the curiosity that drives discovery. Thank you to the viewers who continue to ask questions, to imagine beyond the familiar, and to look at the night sky not just with awe, but with understanding. Your interest keeps the spirit of exploration alive, and it is that spirit that allows us to uncover the universe, one ancient messenger at a time.